Okay. Yeong-Cherng.
Okay, so thank you. I'm sorry for this miscommunications. Thank you, Etiba, for the introductions and also for inviting me to speak in this colloquium on quantum contextuality in quantum mechanics and beyond. So today I'd like to take this opportunity to share with you what I've learned when looking at Wigner's French paradox, and in particular, telling you this no-go theorem that we have derived in this context. So if you're interested in the details of this work, which I wouldn't be able to go through in full details, then here are the coordinates of the publications where we actually put all the details. So the paper was out in about 14 months ago. It's not so recent any longer, but I guess given this audience, this is probably the thing that is maybe most appropriate to talk about here. Okay, so let me start by thanking the co-authors of this work. There are many of them, and at the point when we were working on this and when we wrote all this, they were all at Griffith University in Australia. So this includes the theoretical team led by Howard Weissman and Eric Cavalcanti. I'm especially grateful to Eric Cavalcanti, who actually contacted me and to get me involved in this work. And there was also Anibal Uchera Salakon, the PhD student who was working on the theoretical aspect of this. There's also an experimental component of this work, and that was led by Jeff Pride and his team, especially Nora Titzler, who has now moved to the Free Universities of Berlin. And there was also graduate students, Kok-Wei Bong and Faza Ghaffari. Okay. And before I forget, I should thank my host institute, National Cheng-Kung Universities, who keeps me employed and at the same time also keeping me busy on everything else. Also thanks to the funding agency, National Center for Theoretical Sciences of Taiwan, as well as the Ministry of Science and Technology of Taiwan. Okay, so this work is about Wigner's French paradox. So the first thing that you might wonder, if you have never heard of that before, I mean, probably not for this audience, is that it is something about measurement problem, okay? And at the end of the day, this is about two axioms of quantum theory that don't seem to fit very well together in some sense, okay? So the paradox was initially conceived by Wigner in 1961, to my understanding. But it was only in about 1985 that David Deutsch put it in the form of a paradox. So in this paradox, there are two main characters. One of them is a friend, okay? And I put them in quotation marks because I'm just using that as a placeholder for an observer who is placed inside an isolated lab, okay? And in fact, for a big part of this talk, you see me referring to this friend as Charlie, okay? And the other main character of this story is Wigner. Again, I put that in quotation marks because I'm using that again as a placeholder for an observer who is outside this isolated lab. And in fact, we will refer to this observer as a super observer in the sense that we assume, at least in the context of this paradox, that this observer has the ability to manipulate this entire isolated systems, if you think of it as a quantum mechanical systems. Okay. So what happens in this paradox is that we imagine that this friend measures systems, the quantum systems. And let's say this is a spin half systems, okay? And let's say this friend is measuring the spin observable in the z directions, for instance. Then according to textbook, quantum mechanics textbooks, they will tell you that after the measurements, this observer will assign an eigenstate, which is either the spin up eigenstates or the spin down eigenstates for the spin observable as the post-measurement states of the systems. Okay, so basically here what we have is what one of the axioms tells us, that after measurements, the states goes through this non-unitary probabilistic change. Okay, you have this state update, which is probabilistic after measurements. So in contrast, if you now take the perspective of this outside observer, then what he or she sees is that this is an isolated systems. Then according to the other axioms of quantum theory, then they would see a unitary deterministic evolution of the systems. Right? So in particular, if this, if we have this being the initial states of this isolated systems, I mean everything of these isolated systems except the spin, okay, then this friend will ascribe these particular descriptions as the initial states of these isolated systems. So this is everything else except that as the spin system, and this is the initial state of the spin systems. So what the friend sees as a result of this measurement procedure is just a unitary evolutions, right? And these unitary evolutions will correlate what you have in this isolated lab with some degrees of freedom, the spin degrees of freedom of the systems. For example, if the initial state of spin is spin up, then after these unitary evolutions acting on this initial states, what you get, I mean, for simplicity, I'm not writing, let's say, every degrees of freedom in this lab. Let me just focus on this measurement apparatus. For instance, the display of the measurement apparatus should show up, correlating with the spin up in the systems. I mean, you can go through the math. It's very similar. If it's initially spin down, then of course you get down, tensor down instead. So by the linearity of this unitary evolutions, as you can imagine, then what gets really get us into the problem is that if you have the system being prepared in these superpositions of up and down, then these unitary evolutions will bring it into an entangled state between the spins and let's say everything else in the isolated systems. Okay, so now we see that we are having some kind of inconsistency because according to the friend, he's going to see this or this as the post-measurement states, okay, which is in definite up or down. But according to this super observer outside, he or she is going to see an entangled states describing the whole thing. And in particular, the spin itself is not in a definite up or down states. Okay. So in particular, if quantum theory is universally valid, so that you believe that quantum theory can be applied to these systems, can be applied to the entire thing, then you are going to see, and moreover, if the collapse of this wave function, collapse of this quantum state is objective, it's an objective process, then we're going to have contradictions, right? Because the friend outside sees some change in the wave function, and the change in the wave function results in this, whereas the friend, the observer inside sees this as the final wave functions. Okay, so in principle, this outside observer, he or she could perform a measurement in the basis that's given by this, I mean the projector onto this, and the complementary projector into the entire space. Okay, and that's not going to be the same as consistent with this description that we are seeing here. So that's basically in a nutshell what the paradox is, right? And maybe some of you would you know, or has been told in the past that, well, this is not a problem because you have this decoherence program, it will just solve everything. Okay, there's no measurement problem because the decoherence programs tells you that how the superposition gets suppressed and so on. But not quite, because it doesn't quite tell you how, let's say, this multitude, in this case, two possibilities of measurement outcomes being eventually somehow singled out into either this or this. It doesn't tell you that, okay? So it doesn't solve the problem. But still, this is an old problem. I mean, people have thought about this for a long time. And people have come up with various ways to try to get around this. And let me just try to quickly go through some of the things that people have thought about. For instance, you can get around it by thinking that by rejecting the idea that the measurement outcomes have a single and particular observer independent values. Okay, so for instance, if you subscribe to the relative state interpretations of quantum theory, then you say that, well, this is not a big deal because with respect to different observers, they ascribe different wave functions anyway. For example, for people who believe in cubism, and I think this is not a problem at all. Or if you believe in the many worlds interpretation, this is also not a problem because you don't have this objective collapse of the wave functions. Okay, so there's no objective collapse, and basically this is how they get around the problem. But if you think about no objective collapse, then these are not the only candidates. For instance, you could also have, let's say, in Bormian theory, they also don't believe in objective collapse of the wave functions. Okay, you have a deterministic hidden variable theory that tells you how the outcomes are decided. Okay, and throughout the wave function never collapses. Okay, but you pay the price that you must have some kind of non-local features in this theory. Okay, so you could also be thinking about some other ways to get around the problems by, let's say, postulating the impossibility of having macroscopic superpositions. Okay, because that seems to be part of the problem. For example, you might be thinking that maybe the unitary dynamics of quantum theory has to be modified at a larger scales, like this. Okay, so you might want to modify that, and in one way or another, okay, you might have this spontaneous collapse models, gravity-induced collapse models, or maybe collapse by consciousness, whatever. Okay. So in a way, you get around the problem by rejecting the universality, universal validity of quantum theory. Okay, there are other possibilities, options out there as well, but I don't want to get into them here. So in some sense, one of the contributions that we have in this work is to say that, you know, if you want to get around the problem, then you necessarily must involve some kind of radical relations of one type or another. Okay, so what I get is interesting is that despite the fact that the paradox is an old one, I mean, more than 50 years, but there was a resurgence of interest into all this since a few years ago. Okay, for example, there was the paper by Daniela Frauhigel and Renato Renner, who showed that in some, let's say, sophisticated versions of the Wigners French paradox, then within quantum theory itself, it seems like you are going to have a problem if you believe that the theory also applies to the agents and so on and so forth. It seems like you're going to run into some kind of inconsistencies. And this has led, for example, Baumann and Wolff to conclude that there are actually inequivalent formalisms of quantum theory. And this is actually very well manifested in the Wigner-French paradox. Okay, but for the present work that I'm going to tell you today, these are not so relevant. So the most relevant one is actually the work given by Bruckner back in 2015, when he tried to argue that if you want to have some kind of observer-independent facts, which is, I guess, something that we take for granted. I mean, for people who work on Bell and related stuff, you don't even question that because you take events as something that's fundamental in space-time. Okay, you take that all the observers actually would agree that all these events are real. Okay, you don't even question that bit. Okay, so but for Bruckner, he was trying to argue that he tried to argue in this book that if you want to believe in some kind of observer-independent facts, then that amounts to believing or asking for some kind of hidden variable program. Okay, and then in 2018, he put this in the form of a no-go theorem. Okay, and later on, there was an experiment that is based on this idea that Bruckner came up with. Okay, but there's a problem, and the problem is that already in 2018, it was pointed out by Healy that the notion of observer-independent facts, or at least the way Chosov interpreted this notion of observer-independent facts, seems to be debatable. In particular, it seems like he has come up with a very strong notion of what he meant by observer-independent facts. Okay, and that's basically where we stepped in. We got to know of Charles work, and I think the idea of trying to question whether observer independent facts is something that should hold or not. As I said, it was something that I guess most people take for granted. But so the idea of questioning this itself is interesting, but because of this strong way of interpreting what this notion actually means, I think there's room for improvement, and this is where we stepped in. So to appreciate what he has actually done, I would have to first explain to you some of the things that Charles introduced in his work, Improving this No-Go Theorem. And he introduced what is referred to nowadays as the extended Wigners friend scenario. So here are some of the features of this scenario. So firstly, as opposed to the original Wigners friend paradox, where we just think about a single measurement that's being done in the isolated lab, okay, by the friend. So, and then also by the super observer. Now this super observer actually has a choice over different measurements, okay, just like in a Bell scenario. So we're going to label this choice of measurements by X and the measurement outcomes by A, okay, as in the usual Bell scenario. And as you could probably guess, the other modifications to this is that not only that we have a friend, a Wigner friend, and a Wigner, but actually we have two of this. Okay, so we have another friend here, okay, being placed inside another isolated path. So there's one friend, another friend, and there's a Wigner here, and then there's another Wigner here. And two super observers and two friends being placed inside isolated path. So we're going to imagine at the end of the day, some systems being prepared in entangled states. Okay, part of this goes to Charlie, part of this goes to Debbie, who performs the measurement, and then you have the super observers outside. In the spirit of Deutsch versions of the paradox, we are going to imagine that one of these measurements carried out by the super observer is a special one. So for definiteness, I'm just going to call this the first measurement. So X equals 1, for instance. So what this measurement does is that basically it knocks on the door of the friends of the lab, okay, and then open the door and ask, what is your measurement outcome, or what is the measurement outcome that you observe? Okay, so the super observer asks the friend what measurement outcome he or she actually observes. Okay, and moreover, this super observer is going to assign the measurement outcome of this particular measurements as exactly the measurement outcome that the friend observed. Okay, just going to ascribe the measurement outcome A to be what the friend sees. In other words, I'm going to put it as C. Okay, and of course the same deal here. So there's a special measurement, the first measurement of Bob, such that it corresponds to opening the lab and ask Debbie what the measurement outcome is, and going to assign his measurement outcome in that case as D. Okay, so in general, of course, you can also consider other measurements. Okay, and for the purpose of the present work, there are kind of measurements that we would consider later on, and might as well tell you that now, which is that we imagine situations where this super observer simply, reverse the measurement, because as far as he or she can see, this is just unitary operations, right? So it does time reversal, okay, to actually reverse this measurement done by the friend, okay, and then do whatever that he or she wants to do on the whole thing, for instance. Right. So this is again a special kind of measurement, but it's more general than this kind that I talked about just now. We're just opening the door and ask. Okay, so this is these are some of the ingredients of the extended Wigner friend scenario that we are going to rely on as well. So in this paradigm, Bruckner considered 3 assumptions. So the first assumption is what he referred to as the freedom of choice assumption. And then the second assumption is what he called locality. And in this particular context, as I'm going to show you afterwards, this is, if you like, just parameter independence in the notation or in the notions of introduced by Jared many years ago. So there's the third assumption, which you refer to as observer independent facts. And this is the thing that that I think he wanted to argue against. And in his work, he actually, interpreted it as follows. He just says that, all observables that might be measured, either by an observer or a super observers, are to be assigned a truth value, okay, independently of which measurements Wigners performs. Okay. So remember, I said just now that there's some special status measurement that corresponds to, knocking the door, asking what the measurement outcome is. But there are also some other measurements. Okay, and as of course, many of you will know this very well, that you can have this kind of counterfactual arguments is usually what people would not like so much. Okay, but what Chasaf did here is exactly, saying that, well, I don't care what Wigner is doing, but you have to assign truth values to all these different measurements that he's doing when you wanted to impose this assumption of so independent facts. Okay, and of course, probably many of you would notice immediately that once you have this interpretation of these assumptions, then you can immediately write down a Bell inequality for the super observers. And not surprisingly, this is violated by quantum theory. Okay, and this is how he ended up with his no-go theorem. Okay, but as I say, this is something that is debatable in the sense that if you are to really interpret observer independent facts in this manner, then you are already equating observer independent facts with just Copen's factors, non-contextuality. Okay, independent of the context of the measurements, whether you're measuring this or measuring the other one, I have to assign truth values to all this. Okay, and of course, this is all of you know this very well. This is not compatible with quantum theory. Okay. And if you are to go through this route, then I guess it's clear that you don't need this assumption. Okay? You don't need this parameter independence assumptions at all. Okay, if you go by this, if you take this to mean that this is not relevant anymore. Okay, but maybe what is more serious as a flaw in some sense of this this no-go theorem is that then the objectiveness of the friend's observation doesn't seem to be relevant any longer, because this is strong enough for you to say something. You don't need to care about this anymore. You don't need to care about whether the friend's observation is facts of nature, so to speak. You don't even need that any longer. Okay, so instead we have also three assumptions. Okay. That the first assumption is actually exactly the same one as before, freedom of choice, but my collaborators, they prefer these words, and because this seems to go better with some other papers that they've written, which is fine. And the third assumption, we replace that by absoluteness of observed events. So the essence is the same. We just don't want to get the readers confused, because Chostov has interpreted observer independent facts by something, and we don't want to get the readers confused by thinking that it's the same assumptions. Okay, and of course I'm going to tell you exactly what they are at a mathematical level afterwards. So for convenience, I'm just going to refer to all these three assumptions together as the local friendliness assumptions. Okay, the conjunction of all these three. And our no-go theorem is basically saying that if you assume all these three, and at the same time you assume the universal validity of quantum theory, then you have a contradictions. Okay, so you cannot have all these four together, all these four holding together. Okay, so let me now walk you through these assumptions one by one. So the no superdeterminism assumption, as I said, is just the usual freedom of choice assumptions. And what it says is just that any events on the space-side separated hypersurface are not correlated with freely chosen actions subsequent to X. So as you can well imagine, so in this context, in this kind of Bell-like scenario, which is an extended Wigners scenario, the freely chosen actions are those corresponding to what management choices are made. Okay, And what are these events that enter into this assumption? Well, we are really thinking about the events corresponding to these outcomes being produced. Okay, so clearly, this measurement outcomes is to be produced before the super observer makes choice on what measurement to make, because one of this measurement choice is actually the one that corresponds to opening the door and asking, okay, what your measurement outcome is. So this has to exist first before I talk about this. Okay, in a space-time diagram, okay, maybe this is how you can think about that. And similarly for this. So then in the context of this scenario, then this assumption basically just says the following. The joint probability of all these random variables CD, X, and Y would have to factorize into P of CD and the probability of X and Y. Okay. And in particular, this would imply that the conditional distribution of XY given CD is the same as XY. Okay. So knowing what the measurement outcomes is in the labs, in the isolated labs, it's not going to help you to improve your predictions of these choices of the measurements. Okay. So this is, I guess, the usual formulations of the freedom of choice that a lot of people have seen. So, but from these expressions, okay, you can also arrive at this other expression that says that P of CD given XY is the same as P of CD. And this is actually the form of this assumption that we are going to use afterwards, okay? So the next assumption is the locality assumption. And as I said, you will see shortly that this is maybe something that you will recall to be just the parameter independence assumptions that is maybe more well-known. So what it says is that the probability of an event is unchanged by conditioning on some space-side separated free choice. Okay, again, the free choice would be referring to these things here. Even if this is already conditions on events that are not in the future like points of Z. Okay, so for instance, if I think about the events of this outcome being produced in Alice lab, okay, an Alice measurement device, let's say, then if we are to condition on this free choice, okay, and these are events that are not in the future likelihood of this free choice, okay. So then what this assumption says is that probability of A given CD, X, and Y is just the same as probability of A given CDX. Okay, so knowing Y actually doesn't change anything. Okay, it doesn't change this conditional distributions. Okay, and of course, by symmetry, you have also the other one that says that probability of B given CDXY is the same as probability B given CDY. Okay, finally, let me comment on how this is related to parameter independence. So this C and D here, okay, I may actually formally write them just as lambda. Okay, it's just some dummy random variable. I mean, of course, it has the physical significance corresponding to the measurement outcomes here, but I could just as well replace them by something that I call lambda. And when I write it in this form, then it just looks like the parameter independence conditions that we have seen in the past. Okay, it's like condition on lambda, then the local measurement outcome probability should not depend on the distance measurement choice. Okay, so in that sense, you could see that has no signaling even conditions on C and D. Okay, so let me now move on to the third assumption, which is the absoluteness of observed events. So this just says that when we talk about an event, then this is a real single event, and this is real respect to everyone. Okay, it's not just relative to somebody or someone, but it's actually respect to everyone. Okay, so in particular, it means that in every single run of the experiment, there's a well-defined value for all the observed outcomes. Okay, I mean, in every single run of the experiments, of course, this is observed, this is observed. Okay, because the friend does the measurement. The friend always does some measurements. Okay, but the super observer also always does some measurements. Okay, so for the measurement that he or she does, there's a corresponding outcome. Okay, A and B, and they are also real with respect to the friend, for instance. Okay, so what this means is that there exists a joint distributions of A, B, C, and D for the given X and Y, okay? And this in particular should return the empirical distributions, the correlations, the relative frequencies that you see in the experiments, okay? So this P, A, B, X, Y is something that you should be able to obtain as a sum over this joint distributions, when you sum over all these measurement outcomes in C and D as obtained by the friends, okay? And together with this other feature that I said just now, that the first measurement is a special one, this also imposes mathematically these conditions. So for the first measurement, okay, X equals to 1, because we want the outcome of Alice to be the same as the one for Charlie, okay, because she would just assign her outcome to be the same as the one that Charlie has obtained. So therefore, this is just given by this chronicle delta. Okay, same thing for the other side. The probability of B given C, D, and X, whatever values of X, whenever Y equals 1, then this has to be the same as delta BD. Right? So here are the assumptions as I've just explained to you. And now let's see what these assumptions together entails. What do they actually imply? So firstly, the first observation that I'd like to point out is that with these assumptions, then you find that the set of these correlations, as allowed by the local friendliness assumptions, they are strictly contained in what is called the no signaling polytope. In other words, all these correlations, they satisfy the no signaling conditions, or also called this relativistic causality conditions, back in 1994 by Sandu Popescu. Okay, so to see this, let me just walk you through. So as I said just now, the third assumption, the absoluteness of observed events, would tell you that this empirical distribution has to be the same as what you get when you sum over C and D of these joint distributions. And from here, you can apply Bayes' rule, and that allows you to factorize this distribution into the product of these joint distributions. Okay, but now you can make use of this no superdeterminism assumption, which, as I said just now, would tell you that probability of CD given XY is just the same as probability of CD. Okay, the dependence on XY is not there actually. So you can get rid of that. So that gives rise to this. Okay, now if you wanted to see that it satisfies the no signaling conditions, what do? You sum over the local measurement outcomes. For instance, you can sum over A here, then you'll find that after you sum over A, then of course this is gone. You don't have the A there, so that's what you get here. But you now recall from the locality conditions that this is now something that should not depend on X. Okay, the probability of B of given C dxy should not depend on X. So you get rid of that, and now indeed you end up in expressions that doesn't depend on X at all. And this just the empirical marginal probability distributions on one side, and that doesn't depend on X. Okay, and you can do very similar calculations for the other side, and therefore this shows that they do satisfy the no signaling conditions, and therefore the set of correlations satisfying the local friendliness assumption, they are a strict subset of the no signaling polytope. Okay, so at this point you might also wonder how this set of correlation relates to the set of local hidden variable correlations, because these are both natural subsets of the no signaling polytope. So let me just say that in general, you don't get this reductions from LF to LHV, because LHV will require this further factorizations. Okay, the Bell locality conditions will require this kind of factorizations. But if you compare this with this, okay, even if you are to interpret lambda or CD by lambda, you see that that would require this to be further factorized into something like this. So in general, you don't have, this is not warranted. You don't have anything that allows you to do this factorization. I mean, of course, you can supplement, let's say, this outcome independence conditions into that, and you can get these factorizations. But that's precisely the point. We are not actually putting this assumption into the derivations. Okay, it's not something that's warranted in the context that we are talking about here. Okay, and on the other hand, it's not difficult to show that if you have something that does factorize like this, then it is something that is of this form. So therefore, it tells you that the set of LF correlations, in general, it doesn't reduce to LHV, but it actually contains LHV as a subset. Okay, so therefore you have this inclusion relations here. Okay, so what other things do we know about this set of correlations? It's easy to show that it's also a convex set, and for situations where you have finite number of inputs and outputs, then it is a convex polytope. And again, using these special features, these features of the special measurements here, then you are going to see that the empirical correlations actually take this explicit form. Okay, so make use of this, then you can show that whenever one of these special measurements are involved, then you have this more explicit form. But otherwise, in general, you have, if you like, mixtures of some kind of no signaling distributions. Okay, so in particular, if there are only two measurement choices, and each of these has two measurement outcomes, then it turns out that even though in general this is not the case, this set of LF correlations coincides precisely with the set of local hidden variable correlations. Okay, so in other words, then the only non-trivial inequality describing this set of correlations are exactly just the Clauser or Shih-1-Bell inequalities. Okay, so in this way, it also justify what Chostov has proved in his no-go theorem, even though he has started off with something that's stronger. But what we are saying here is that he doesn't need to do that. He'll get to the same theorem anyway. Okay, if he has done everything without the strong assumptions, the stronger assumptions, let's say. But in general, they're different. And in particular, let's say you allow yourself one more measure, then you find that you can show that this set of correlation, they are described by 96 extreme points, and you can use some software to solve for the facets, the inequalities in this case, and there are 900 over facets inequalities in this case describing this set of correlations. So what is also interesting is that this exact same set of inequalities, they were also discovered independently back in 2014 in a totally different context, okay, by Eric Woodhead under the name of partially deterministic polytope. Okay, so all these inequalities can be further classified into 4 different categories, and here they are. So one of them is what we refer to as Bruckner types inequalities, in the sense that they are two measurements, two outcomes inequalities that always involve this special status measurements on both sides. Okay, so these are genuine local friendliness inequalities, but also at the same time they are facets for the Bell polytope. So when you have 3 measurements per side, then you also have this famous I3322 inequality. So that turns out to be also a facet of the LF polytope, at the same time being the facet for the Bell polytope. So there's also this kind of inequality that we refer to as semi-Bruckner inequalities, because you see that only this special status measurement is only involved on one side, but not the other side. So this tells you that actually an LF inequality can be derived by considering only a friend on one side, but not the other side. So it's also possible to come up with local friendliness inequalities like this. But what is more important for the purpose of our work is that there is some kind of inequality, there's some genuine LF inequalities that are not facets of the Bell polytope. They are still legitimate Bell inequalities, but they are not, let's say, tight inequalities. They are not facets of the polytope. And maybe even more importantly is that if you consider these 3 measurement settings, 2 outcomes case, then there are also facets of the Bell polytope that involves the second and third measurements. Okay, but these are not legitimate local friendliness inequalities, in the sense that these inequalities actually cut through the local friendliness polytope. Okay, let me help you to appreciate this a bit better geometrically. So here's a 2-dimensional slice in this 15-dimensional space, right? So in the green part, we have the set of local hidden variable correlations. And the green together with the orange one, okay, these are the local friendliness correlations, okay, convex polytope. And also very importantly, the red boundary here describes the boundary of the quantum set, okay, which we determine numerically. So the thing that I'd like you to pay attention to is that the set as described by quantum theory and the set that you obtain from the local friendliness assumptions, they are not comparable, okay? So for example, here you see that the local friendliness set actually sticks outside the quantum boundary. But on the other hand, here you see that the quantum set sticks outside the local friendliness boundary, okay? So in particular, you could have violations of this local friendliness inequalities, okay? So that's all about the theoretical side. And let me now just briefly talk about these experiments that the team at Griffiths has done. So here's the experimental setup that I'm not going to explain a lot. All that maybe I wanted to say is that they use continuous wave laser sources to produce photons that entangle in the polarization degrees of freedoms. And the state that it produced basically looks like this, okay? It's a mixture of the maximally entangled states and some other product states that are in the horizontally polarized and the vertically polarized product states of this form, okay? So this parameter mu is controlled by this halfway plates here, okay? By tuning a setting there, you can change this, okay? What's more important here is that here, the friend in this context is actually played by the path of the photon, okay? So we have photons being produced through this setup, okay, entangled photon pairs. So one of them would go through one side, the other one go to the other side, okay? So if you like, you could see this as where Charlie is in action, and this is, and we are playing the role of Alice, for instance, and here this is Debbie, and again, we are playing the role of Bob, okay? So in the sense that these optical elements here would entangle the polarization degrees of freedoms of the photon with the path degrees of freedoms of the photon. So if we wanted to ask the friend what the measurement outcome is, like what we do in this special status first measurement, what we do is that we put these motorized mirrors here, blocking the path, because at this point, the path degree of freedom is entangled with the polarization degree of freedom. So if this is indeed here, then they will be reflected differently. And then we just need to check which of these detector clicks, and then we read off the values of the measurement outcomes, okay? So if we don't want to perform this particular measurement, we could perform some other measurements. And the one that we consider, as I said earlier, is first to perform a reversal of this, okay? And this is done by just moving these mirrors aside, and then the photons won't be reflected, but they will go straight through. And after these optical elements, they will converge again back to a single path, okay? And then you can continue with whatever measurements that you wanted to do afterwards. Right, so here's a plot of the experimental results. And you don't need to look into all the details here. So basically, as mu gets larger and larger, we get closer and closer to a maximally entangled 2-qubit state, okay? Meaning it's less and less noisy, all right? So therefore, at the beginning, you see that none of these inequalities are violated, okay? So here is the border. So to have a violations, you have to be up here. You have to be up here. So you see that as mu is small, we don't have any violations. All these are below this horizontal line. But as we increase mu, then we see that more and more of these inequalities are violated, and eventually all these inequalities are violated, okay? And what I would really like you to focus on is actually these two data points, because what you find is that they show violations of Bell inequality that is not a local friendliness inequalities, okay? And in fact, we checked that this data here, they don't violate any of the local friendliness inequalities, okay? But at the same time, it violates some Bell inequalities. So this says that these correlations here, they are not inside the set of local hidden variables correlations, but they are actually inside the LF set, okay? And therefore, this is an experimental demonstration of this strict inclusion relations that I talked about earlier. So let me now conclude by saying that we have been, in the context of Wigners-Friendly paradox, we consider this local friendliness assumptions, which is a conjunction of three assumptions: the absoluteness of observed events, no superdeterminism, and locality in the sense of parameter independence. And we show that they are not compatible with certain quantum predictions in this extended Wigners-Friends scenario. We have also characterized the correlations respecting these assumptions in a theory independent manner, okay, or if you like, device independent manner, in the sense that we only need to look at correlations, okay? And or we show that we have these kind of inclusions and relations. So we also characterize completely this set of correlations in an extended Wigners-Friends scenario when you have three measurement choices with two outcomes. And we have also looked into characterize this inequalities in the sense of the quantum violations, but I don't really have time to talk about it here. And finally, we also carry out an experimental simulations with the friends represented by photon paths. So why do I say simulations? Because I guess when you think about what how I introduced the Wigners-Friends paradox, then you probably would expect some kind of macroscopic observers for the friends. And probably for many of you, the path of a photon is not macroscopic enough. So this is at best simulations. Okay, so if you are interested in the details, then they are again available in these publications. So I guess I have talked enough, and thank you very much for your attention.